Here is section 10.8 where we look at the idea of angular momentum. Our objectives here are to define angular momentum and identify its role in rotational motion. We want to use various forms of the angular momentum equation and find this variable in several types of systems. So first of all, we need to ask ourselves if rotating objects have momentum to them. That answer is absolutely yes. Just like any object with mass that is moving has a kinetic energy, an object with mass that is moving also is going to have some sort of momentum. Now, although an object might not have a linear momentum, since its center of mass may not necessarily translate through space, a quantity of motion is still associated with that rotation, and we call that angular momentum. So something that is simply just spinning around in a circle, like a CD, can have an angular momentum to it, even if it isn't translating or moving in a certain direction. That spin in and of itself would be considered an angular momentum. So angular momentum is denoted with the variable capital L. If you imagine a particle of mass m moving with some sort of momentum at a position r, that's how we define angular momentum. Relative to the origin, we define L as r cross p. Remember, we've already defined the cross product now, so we know that we can define variables in that way. So r cross p would be our definition for angular momentum. The units for this would be the kilogram meters squared per second. And I want you to note that both magnitude and direction of L are going to depend on the choice of the origin. In the picture that we have in the top right hand corner here, we can see that we have an origin in our system, and there's some mass that is moving with some angular momentum to it, and we can now define the angular momentum of that. Notice that the direction of L is actually perpendicular to this system, perpendicular to the plane with R and P in it. So again, it is very much like some of our other rotational variables, where since the XY plane is taken up with some of these position values and a momentum value that can actually be changing direction throughout X and Y, we define L to be along the Z axis. So again, you can see L here in terms of direction being that R cross P. Now, since L is a cross product, it can be written as a cross product. Remember, we define the cross product as taking the magnitude of the first vector, multiplying it by the magnitude of the second vector, and then multiplying by the sine of the angle between them. That means that we could also define L as the magnitude of R, or just an R, multiplied by the magnitude of P, which P is an MV quantity, and then multiplying by the sine of the angle between them. So L could also be defined as MVR sine of theta. So what happens to this angular momentum value when R is parallel to P? If R and P are in the exact same direction, coming back up to this drawing, R is going this way and P is also going this way, we would see that the angle between them is a 0. And the sine of 0 is going to give us a 0. So when they are parallel, you get nothing. It's just like with any other cross product. If you were to try to cross two values that were in the same direction, just like with torque, you would get a 0 value for that cross product. But if R and P are perpendicular to each other, then you would take the sine of 90, which is 1, and you would maximize your angular momentum equation to equal mvr. Now, this could be true of a single particle. It could be true of a disk that is rotating like we showed up here, but it could be true also of any particle that is moving at some distance r away from another object with a momentum. So what I'm saying is that you might even just talk about a person with maybe a plane flying overhead. And this plane can have an angular momentum about that person as the person being our origin, simply because the plane is some distance r away from the person and is moving with some momentum p. We can simply take the mass and velocity of the plane and multiply by essentially the altitude of that plane and talk about the angular momentum of that plane as it passes overhead above the person. So we are not only talking about, rotating disks or wheels, but we can also talk about single objects that are moving with any sort of momentum some distance away from an origin. So for translational motion, we found that net force could also be set equal to dp dt. We're going to find something very similar with rotation. Instead of net force, we're now talking about net torque. Instead of dp dt, we're talking about dl dt. And you can see the proof to this on page 314 in your books if you would like to follow that along and find that. But it is true that you can find these values to work out that way, where the net torque is equal to a change in your angular momentum per time. So essentially what we're saying is that if your angular momentum is going to change with time, it is due to some sort of net torque on the system. Angular momentum will only change in time if there is some sort of a torque on that system. Now, this idea is only valid when torque and angular momentum are on the same axis. Again, we have them along that z-axis typically. And it can be valid with several forces that may be acting. So if you had a system of particles, the total angular momentum could simply be the angular momentum of all the particles added up. So there could be several forces acting on several different particles. Simply find the L value for each individual piece, add it all up, and you will have a total angular momentum. Now this total can vary with time if there is a net torque on the system, a net external torque. So when you sum up all of the torques on your system, that will be equal to the change in momentum, the change in the angular momentum with respect to time. Now note that this is valid even when the particles move relative to each other. We never had to impose the rigid object model to come up with these values or these equations. So if we did take a look at a rigid object, we could say that each particle is going to have its own angular momentum. Each particle is going to have its own little bit of mass, moving at some velocity at some distance, a little mvr. Now if we were to sum up all those little mvrs, we could take the r, or the v that we have in this equation, and rewrite it as an r omega, knowing that v is equal to r omega, as we looked at how translational variables correspond to angular variables. And then we could actually pull the omega outside of the summation, because that omega is the same for every little particle or every little bit of mass, which leaves us with a summation of mr squared. And hopefully you're starting to recognize that quantity, because that mr squared is the I value, that moment of inertia, which means that we actually have another way of expressing angular momentum. Besides r cross p, besides mvr, we can also express angular momentum as an I omega. And that's another way that we can find that value. So let's look at an example where we can use this new knowledge. Remember this one? The Atwood machine, right? We just did this example again when we looked at the sum of the net torques, and we summed up forces, and we figured out what the acceleration of this system would be. We're going to do the exact same problem, but we're going to think about this system in a different way. We're going to use angular momentum as our approach this time. Now, if we're going to use angular momentum as our approach, we need to choose an axis that this is all rotating around. So our axis is going to be the center of the pulley. We're going to look at how everything rotates or moves around this center point and what its angular momentum would look like around that center point. This problem is also going to be different in that we're going to look at this entire thing as a system. All forces inside of this system would be internal to the system. And when we look at the consideration of angular momentum, we need to remember that as we look at the sum of the external torques being equal to the change in momentum with respect to time, that we really only care about external forces. That means that all of the tension forces that we were analyzing in these areas here are now going to be forgotten about or ignored, really, because they aren't external to the system. We're treating this as one big system, finding its total angular momentum, and then looking at how that momentum changes with time to set it up in this equation that we have here. So let's talk about total angular momentum. Total angular momentum is going to be the sum of the momentum of all of these pieces. M1 is going to have an angular momentum about the pivot point as it's moving in this direction here. And as it moves, its angular momentum would be given by its mass times its velocity that it's moving at times this distance r away. As we look at its line of motion is a distance r away from the pivot point. So we have an m1 vr. For object 2, also its line of motion is a distance r away from the pivot point, and therefore its angular momentum would be an m2 vr. Again, they'd be moving at the same velocity since they're connected by that string. And we are going to have this still be a pulley that is actually rotating and turning because of the different tensions on either side. And that means that if this is a pulley that's actually rotating and turning and has friction to it, then there's also the angular momentum of the disc itself rotating around its axis or its pivot point. So we're going to also have an I omega value that is going to be plugged in here too. Now we're going to simplify this a little bit. So L is going to be an M1 VR plus an M2 VR. The I of the pulley itself, remember, was a 1/2 M R squared. And omega, again, because V is equal to R omega, omega can be rewritten as V over R. So again, we'll simplify, cancel one of these out. Since everything has this R, we could actually pull the R outside, and everything has a V, so we could pull the V outside as well. So we really have an M1, an M2, and a 1/2 capital M, all being multiplied by a V and an R. Now we can finally come back up to this equation. We want to look at the net external torques on this system, and the external torques are only gravity acting outside the system pulling on this. So we have an M1G times a distance R or lever arm R away, and we also have an M2G times a lever arm of an R. So if we were to sum up all those external torques, we would have M1GR minus M2GR, because M2 would cause it to rotate in the negative direction. Now this can be set equal to a dl dt. So we're looking at the time rate of change of all of this M1, M2, 1/2 M, and VR, and how that changes with time. Now as we look at this, the only thing that's going to change with time is the V value that we have here. The R values aren't going to change with time. The M values aren't going to change with time. So really, I can write my equation as an M1 plus M2 plus 1/2 of capital M, and then multiply that by the R and dV dt. And of course, what is dV dt? Well, really, we could just write that as an A. Now we can take this equation, solve for the A. If you want to pause the video here, take a second and go through the algebra. You'd find that your R's again would cancel out. And as you solve for A, you would get the exact same solution as we got before. M1G minus M2G all over M1 plus M2 plus 1/2 capital M. We end up with the exact same solution, but just approached in a different way.